Good morning, guys. 1 second, get some things organized here and we'll get started. There we go. Oh, it's not running. Oh. Come on. There it is. Wakey camera. All right. So welcome back to Calc 1, lads and ladies. Today we're going to continue talking about some applications of the derivative. Fairly simple stuff. But there's a technique I wanted to show you guys that I haven't shown you yet. And it's not a huge thing. So before we get back to looking at like related rates, those sort of applications, I just wanted to show you one last little differentiation trick. There are a few problems in your homework that ask you to use this. And I think they might even show up before the related rates problems. I don't remember the order I put them in there. But I think they show up before the related rates problems. So I'm sorry, I intended to show this to you before talking about related rates, but we haven't yet. Today is the 19th, February 2021. And today we're going to do two things. We're going to do some more related rates. And we're also going to talk about this tool called logarithmic differentiation. Okay. Logarithmic differentiation doesn't have its own section in the textbook. There's a section in the textbook called log derivatives, which is different. It's like derivatives of log functions. But I want to kind of spend a second wandering through this special trick. So first, yeah, log derivatives and logarithmic differentiation, which I'm just going to abbreviate as diff. So we can say diff differentiation. It's a long word. Okay, so we would know that the derivative d dx of the natural log of x is 1 over x. All right, this is something we showed with the chain rule a while ago, right? We can expand this to other base logs. Using the change of base formula. And hopefully you guys remember the change of base formula. It says that the base b log of x can be written as the base c log of x over the base c log of b. So if you want to go from one base to another, like you're given a base 2 log and you want to go to a natural log, something like that, you can use this change of base formula. A special case of this of which says that the base b log of x is equal to the natural log of x over the natural log of b. All right, so here I'm choosing to use for the letter C over here, for the quantity C here, I'm plugging in the number E. So the base C on the right-hand side that we get to choose in the change of base formula, I'm using E there. So it says you can take any base logarithm, base 2 log, base 5 log, whatever, and rewrite it as a natural log. It's worth noting that the natural log of B is a constant. So you might think of this like this. It's the natural log of X with this constant 1 over ln B out front. So if I wanted to differentiate some other base logarithm, how's that going to shake out? Well, I just have to differentiate this thing instead. All right, I'm going to hold here and let you guys think about how we would differentiate that. I see there's a question in chat, or comment in chat. After the word special case of which. So a special case of which says, so sort of here's the change of base formula in its full generality. This says if somebody gives you a base B log, then you can rewrite it as a base C log where you get to choose the number C. So if I want to take a base 2 log and rewrite it as a base 7 log, the base 2 log of X is the base 7 log of X over the base 7 log of 2. That's the idea. And so I'm using this formula, a special case of this formula, right, where I plug in E for C. So that's what I mean by special case, to get this. So any base logarithm can be rewritten as the natural log divided by the natural log of the old base. And my aim is to find, like I know how to differentiate ln x, so I want to know how to differentiate this guy. And the trick is going to be to rewrite this guy as a constant times ln x. So now that we're down here, my goal was to find the derivative of this other logarithm. What would be the derivative of this expression? Do I need any particular rules?
Would it just be the product rule?
It's a fair question, right? So that's kind of what I'm asking. Like, do I need the product or quotient rule here? And kind of the thing I want to emphasize is that this piece right here is a constant. This guy is a constant. Not just the one, but the whole 1 over ln B thing, the whole thing. So I don't actually need any sort of product or quotient rule, just like differentiating 2 ln x or 7 ln x. The constant multiple just comes along for the ride. We'll have 1 over ln B times 1 over x. Because the derivative of ln x is 1 over x. And that's it. I.e., the derivative of some other base logarithm, the base B logarithm, where B is any number of your choosing. You might rewrite this as 1 over x times the natural log of B like this. This is often how you'll see it written. So this is fun, but it's not really the main point of the logarithm discussion. I just wanted to show you how to differentiate other base logarithms. Think of it as a sort of warm-up. Any questions on what we're doing here? What we did here? Okay. I'll hold here for just a few seconds in case anybody is writing, and then I'm going to show you logarithmic differentiation. So what does it look like to apply the chain rule to a natural log? What if I want, oh, yeah, here, let me back up for a second. So what we're really doing here is just finding the derivative of another base logarithm. So let me insert a little example after this. I'll talk through this again one more time real quick. The goal is, okay, I know how to differentiate the natural log of x. And with the chain rule and product rule, I can differentiate other combinations of things involving the natural log of x. But what about other base logarithms, right? Like you guys learned in your algebra classes about a base 10 logarithm. That's called the common log, or the base 2 logarithm, the binary log. We'd like to know, are there other ways that we can, or other logarithms that we can differentiate, right? These other log functions exist. So what are their derivatives? The natural log's derivative is 1 over x. So what's the base 2 log's derivative? We're able to use this change of base formula to get this formula. This is the formula that you need to remember. It's just a new differentiation rule. It's a new differentiation formula. It's like we remember the derivatives of ln x. We remember the derivatives of the trig functions. Here's the derivative of the arbitrary base logarithm. An example where we might use this, and I'll come back to the other example in a second, be so I want to calculate d dx of the base 3 log of x. Well, and this one's just, I'm just going to apply this formula right away. All right, so it tells me that the derivative of the base b log of x is 1 over x times the natural log of b. So the derivative of the base 3 log of x should be 1 over x times the natural log of 3. All right, that's all. We could use this in concert with other things, like find d dx of x times the common log of x. You guys all remember that the common log, the log log, this is really a base 10 logarithm. So if I want to find this derivative, I'm going to need to use the product rule. When I differentiate the x, I'll have a 1. So this is going to be 1 times the logarithm function left alone. And then I add that to what I get when I leave the x alone, and when I differentiate the logarithm function. This log log is a base 10 log. So following this formula, just like we did here, we'll have 1 over x times the natural log of 10. And then in that second expression, these x's are going to cancel. This is log x plus x over x times the natural log of 10. Let's do it like this. And then here, this x over x, they'll cancel, and we get log x plus 1 over the natural log of 10. So that's all we were doing on that first page. Just cooking up this new differentiation formula that lets us expand or generalize a little bit the types of log functions we can differentiate. Does that feel a little more comfy? Cool. So the place this really gets fun is when we start interacting with the chain rule. That was the thing I had written on the previous page. I'll just continue it here. What if I wanted to find ddx of the natural log of sine x? Of course. This is a chain rule thing. And I noticed from the exam, the chain rule and trigonometry are places where we definitely get a little bit nervous. So I'm going to take a second. This is my inner function here. U. And this is the outer. So here's inner. This guy right here is the outer. So it's kind of purple kind of means he's dead. So the derivative of ln of some stuff is going to be 1 over that stuff, right? Derivative of ln x is 1 over x. This is going to be 1 over the sine of x times the derivative of sine x. And the derivative of sine x is cos x. So this is 1 over sine x times cos x, which is, I can multiply these. This is cos x over sine x. And if you guys will allow, I would like to kind of figure out a maximally general chain rule thing here. So instead of looking at like natural log of sine of x, I'd just like to know what happens if I find a formula for the derivative, or can I find a formula for the derivative of the natural log of u, where u is some other like inner function, not necessarily sine of x. Now, kitty, no, it's not your food. One of my cats is way too greedy. So let's do that.
Can I ask you a question about that really quick? So for the chain rule, it's the derivative of the outer times the derivative of the inner. So does that
The
become
chain
1
rule
over
says
sine x?
if you're going to differentiate like f of u of x like this, that you differentiate the outer, leaving the inner alone. So it's the derivative of outer with the inside chilling. Then you multiply by the derivative of the inner. So this isn't multiplication here. This piece is function notation, right? This is the outer function differentiated with the inside piece left alone. That's like 1 over sine x here. And then we multiply by the derivative of the inside. So what was the question? I'm sorry.
Oh, wait, not okay. I think I might have had it confused this whole time. Okay. So I thought the derivative of the outer is 1 over sine x. That's what I thought you were saying.
Yeah, this is the derivative of the outer with the inside left alone. And then we're multiplying by the derivative of the inside here. So this piece, the sine of x all primed, that's like u primed. And
Yeah.
1 over sine of x, that's like f primed of u of x. Is that sitting well?
Okay. I don't know.
So kind of think of it like this, right? Cover up the signs, yeah? If this was natural log of x, the derivative of natural log of x should just be 1 over x, right?
Yes.
So the derivative of the natural log of whatever's under my finger here is like 1 over whatever's under my finger here.
Okay.
But then we have to multiply by the derivative of the inside. So the derivative of natural log sine x should be like 1 over sine x.
Mm-hmm.
That's the derivative of the outer. But then
Yeah.
by the chain rule, I have to multiply by the derivative of the inner function.
Okay. Okay. Yeah, that makes sense now.
And more generally, kind of the nice thing here, in general, And this piece is the tool that we're going to use for our logarithmic differentiation in general. If u equals u of x, right? It's just some function. It is a function. Then the derivative d dx of the natural log of u is 1 over u times u primed. The way I actually like to remember this is as u primed over u. So if you want to differentiate the ln of some shit, it's the derivative of that shit divided by that shit. Stuff primed over stuff. And that's what we see here, right? The derivative of the natural log of sine of x is the derivative of the sine of x over the sine of x. U primed over u, where u is the sine of x.
Okay, thank you.
Yeah, of course. So this formula down here, this recipe is the one that's going to allow us to do some cool stuff called logarithmic differentiation. So any questions up to here? This is kind of the warm-up. What we're going to do is combine this with implicit differentiation. When you combine this with implicit differentiation, and that's going to allow us to escape using the quotient rule or the product rule, especially in some cases where you really don't want to use the quotient rule or the product rule. Let me show you an example. You have something like this in your homework. Let's find Nala, no kitty. Oh damn, sorry. Sorry, find y prime. Tearing up the couch. Where y is equal to let's do tangent to the 7 times, how about sine cubed all over x squared plus 3 to the 4, something like this, all right? This looks unpleasant. Normally, to differentiate this, I would need the quotient rule. And then within my quotient rule, every time I need the derivative of the top, that's going to be like a product rule and a chain rule. And every time I need the derivative of the bottom, that's like a chain rule. So to differentiate this normally, I would need quotient, product, and chain rules. And they're nasty, like it's shitty. Just the derivative of the top is complicated enough on its own. So wouldn't it be nice if there's a way to get around it? So differentiating this normally, I'll say diffing this normally. Would require the quotient rule, the product rule, product rule, and the chain rule. Chain rule twice. Actually, chain rule 3 times. It's nasty, right? You need a chain rule when you go to differentiate tangent to the 7. You need a chain rule when you differentiate tangent sine to the cubed, and you need a chain rule when you differentiate this piece. And it's not like you can just differentiate those pieces on their own. You have to set it up with the quotient rule first. So it'd be like the bottom times the derivative of the top. And then when you go to take the derivative of the top, you need the product rule. And then within that product rule, you need the chain rule. Each time you differentiate one of these things, you're going to need the chain rule. Then you have the top times the derivative of the bottom. Okay, well, the derivative of the bottom, that's another chain rule. And then you have to divide all of that by the bottom squared. Fuck that noise. Fuck it, it sounds awful. This is awful. And it's easy to make a mistake. Easy to make a mistake doing all that. But I still need to find y prime. So instead, we're going to take the log, the ln of both sides. And expand. Then differentiate. So the miracle of the logarithm function is that it has all these really cool algebra properties. So if I take the log on both sides, I can use the algebra properties of the log to expand this expression. Once I've expanded this as far as I can, each of the little pieces will be much easier to differentiate. So that's going to be the move. On the left-hand side, I'll just have the natural log of y. On the right-hand side, I'll have the natural log of the 7th power of tan x, the 3rd power of sine x, all divided by x squared plus 3, quantity to the 4th. Now here's where we check if you guys actually learned this stuff in college algebra, pre-calculus. There's a reason we said you needed all those log properties. This is it. First I can say, okay, well, this is the log of the top minus the log of the bottom. Sorry, I'm using the word log to refer to the natural log, ln of the top minus the ln of the bottom. Does everybody remember this rule? The ln of a over b is the ln of a minus the ln of b. And now I've got some more rules I can apply. This piece, if you have a log of a product, the ln of a times b is the ln of a. So that's the ln of tangent to the 7 plus the ln of b. That's the ln of sine cubed. And then I still have this ln of x squared plus 3 to the 4. And then one last bit of simplification before I differentiate, I can pop these powers down, right? This power, not the 2 here, but this 4 here can come down. So this is 7 times the natural log of tangent x plus 3 times the natural log of sine of x minus 4 times the natural log of x squared plus 3. So ln y is equal to this. And I think you would all agree, I know I feel strongly that this is much easier to differentiate than the nasty thing I started with, because each of these is just like one little piece. It's just one little rule. Each of these needs the chain rule, but it's a little chain rule.
What
And we
was
have our formula.
that first rule where you took it and made a subtraction?
Yeah, so let me go ahead and recap the log rules. That doesn't sound like a bad idea. So I don't want this to interrupt the workflow of this problem, right? So make sure, if you're gonna write these log rules down somewhere else, make sure you put them somewhere in your notes that is like accessible, but doesn't interrupt this problem. So leave space after this. We're gonna finish this problem stuff. But the log rules, I'll just write them down in terms of the natural log of a over b, natural log of a minus the natural log of b, natural log of a times b, is the natural log of A plus the natural log of B, and the natural log of A to the B power is B times the natural log of A. 1, 2, 3. Here, I used rule 1, rule 1 to turn the fraction inside to subtraction outside. And then here, I used rule 2 to turn this multiplication inside into addition outside. And then here in each of these pieces, I used rule 3 to turn the powers inside into constant multiples outside. So these log rules, they're important. They really are. Logarithms, hugely important functions in mathematics in general, but especially in calculus. If you want, I have a worksheet for logarithms that can serve to kind of reboot your log powers. So if you want your logarithm skills to return, it's been a little while since you've had to do something with them, send me a message on Canvas or an email. I'll send you this worksheet. It's really good. I do have to return to the problem here. So are we comfy with what was done? This big division bar inside the logarithm, log of something over something else, is the log of the top minus the log of the bottom. And then the multiplication in here, these two things in the top are multiplying each other. So the multiplication inside the log is the same as addition outside the log. Log of A times B is log of A plus log of B. And then this piece just still chilling. And then finally, I bring the powers down in. So this is tangent of x all raised to the 7th power inside the logarithm, so that 7 can come down. This is the sine of x all raised to the 3rd power inside this logarithm, so the 3 can come down. And this is x squared plus 3 all raised to the 4, so the 4 can come down. Now the magic. Right, so right now I have the natural log of y equals, versus this. The natural log of y equals 7 times ln 10x plus 3 times ln sine x minus 4 times ln x squared plus 3. So if I differentiate on both sides, what do I get? Let me write this down over here, and that way I can show you the rule on the other end. So we'll take the derivative on the left. I'll have d dx of ln y equals d dx of 7 ln 10x plus 3 ln sine x minus 4 ln x squared plus 3. Now, we can use this rule. So how do you differentiate the natural log of some shit? Well, it's that shit primed over that shit. So on the left-hand side, the derivative d dx of the natural log of y, that's y primed over y. And on the right-hand side, this is going to be 7 times the derivative of ln tangent. Well, the derivative of the ln of tangent should be the derivative of tangent over tangent. That's secant squared of x over tangent x plus 3 times the derivative of ln sine is the derivative of sine over sine minus 4 times the derivative of ln x squared plus 3 is going to be the derivative of the inside, which is 2x over the inside, x squared plus 3. And that's all the differentiation, right? Easy, very easy. No big differentiation rules, nothing complicated. Certainly you don't have to use the quotient product and chain rule here. You just have to use the chain rule. Finally, if I want an explicit expression instead of an implicit expression, this is an implicit expression because there's a y here. I can multiply this y back over and then substitute in. You get y prime equals y times 7 secant squared x over tangent x plus 3 cos x over sine x minus 8x over x squared plus 3. And then what was y? Well, y was my original function. Was I can't fit it in here. Tangent to the 7. So this is tan of 7x sine cubed x over x squared plus 3 all to the 4 times, and now this piece, 7 secant squared x over tan x plus 3 cos x over sine x minus 8x over x squared plus 3. And that's it. That's y prime. I think you would agree that these, all the differentiation is like right here. This is the whole thing. That's the only spot where I had to use any differentiation rules. Everything else is just algebra. And it's relatively simple algebra. You know, no like crazy factoring, no like common denominator work. Nothing too intimidating. And that's why logarithmic differentiation is so awesome. Because it lets us find the derivative of something scary looking, right? Finding the derivative of this is the original piece right here. Finding the derivative of this would be frightening on its own. It would be a lot of work. But if you take the log and expand before you differentiate, you can avoid all of the rules associated with products and quotients. Questions on this example? Is there anything we'd like to look at more carefully? Are there any pieces here that we're wondering about?
Can you explain how you got 2x over x squared plus 3?
Oh, so I'm following that rule that says like the derivative of the natural log of u is u primed over u. So here I have the natural log of x squared plus 3. So his derivative should be the derivative of x squared plus 3 divided by x squared plus 3. So yeah, u primed over u. So the derivative of x squared plus 3 is 2x. So I've got 2x over x squared plus 3. Yeah, it's a really nice trick. Alrighty then. Let me pull up your textbook here. That's all I have to say on logarithmic differentiation. There's 1 or 2 problems in your homework that'll have you playing around with that stuff, and it's good. I think you'll enjoy it. It's not terribly hard. The other thing I want to do today is just get us more practice with related rates. I know that implicit differentiation, the reason we do all this stuff together, logarithmic differentiation and related rates, is because it all gives you practice with implicit differentiation, which I know is a little bit tricky as you're first getting used to it. So let's come in here. We did the ladder problem on Wednesday, right? We can do the cone one. There's a more fun one here, I think, somewhere. Yeah, let's do one with some trigonometry. Let's look for a challenging one. That one's okay. Yeah, we'll do one fun one here with some trigonometry. And then we'll do one that is just straight up pure math. So let's look together at number 13 from the textbook. I'll write this down. This is a related rates problem. So a plane flies over a radar station. Altitude 1 mile and ground speed 500 miles per hour. Find the rate of change, the distance to the plane. Oh, actually, this isn't the one I was thinking of, but that's okay. Yeah, hang on. The distance from the plane to the station is increasing when it's 2 miles. Okay, we can do this. Find distance from changing that distance along the 2 miles station. So you've got a plane and it's flying over a radar station. The altitude is 1 mile. And the ground speed of the plane, the speed the plane's going like relative to the earth beneath it, is 500 miles an hour. We want to find how fast is the plane's distance from the station increasing at the moment when that distance is 2 miles. Maybe here's my radar station. And here's my plane. All right, and it's 1 mile above the station. I'm just gonna keep the units here. And we know he's going this way. And we know that sometime later, he'll be over here. I'm going to use the nose of the plane as my distance marker. Now we're right above. Later we'll be over here. They say they want to know how fast is the distance from the plane to the station changing that's this distance. I'll call it L. I don't want to use the word letter D anywhere in here because the letter D is reserved for the derivative. But the nice observation is that this forms a right triangle. It doesn't look like a right triangle. It's a right triangle. They want to know at the moment when L is 2 miles, what is dl dt? So what do we want? We want dl dt when L is equal to 2. Okay. The other thing we should label here, of course, is the distance from the plane has gone from its spot overhead the radar station here. So I'll call this distance x. I know that dx dt, the speed at which the x is increasing, right? If the plane is flying this way, then x, which is the distance from the spot right above the radar station to where the plane is now, that's certainly increasing. And the speed at which it's increasing is 500 miles per hour. So x is growing, so dx dt is positive, and it's growing at 500 miles every hour. So dx dt is 500. And the question is, can we use this information to find dl dt at the moment when L is 2? The nice observation here is that we do have a right triangle. This is 1, this is x, and the hypotenuse is L. So we know that 1 squared plus x squared is equal to L squared. Or just 1 plus x squared equals L squared. So I applied ddt to both sides. The time derivative ddt of 1 is certainly 0 because 1 is a constant. What about ddt of x squared? Remember, x does change over time.
It will be 2x dx dt.
Perfect. If this was ddx, then we would just have 2x. But it's ddt. So we're differentiating implicitly here with respect to t. So you kind of have to treat the x's the same way you treat the y's in our other implicit differentiation problems. We're differentiating with respect to something other than this variable. So you have to multiply by the derivative of that inner thing. The inner thing here is just x. And the ddt derivative of x is dx dt. On the right-hand side, we have a similar thing. We're going to get 2L dl dt. We can divide both sides by 2 if you want. We get x times dx dt equals L times dl dt. Is everybody comfy with where we're getting this? Okay. So let's refocus on what we want and what we know. We want dl dt at the moment when L is 2. I know that dx dt is 500. So I can plug in 500 for dx dt. I can plug in 2 for L, but I still need to figure out x. This happens often in these related rates problems. You get here, and then you have to ask yourself, what is it I need to finish the problem? I divided both sides by 2 for this. So I can divide both sides by 2's and the 2's go away. So what I'm going to do is say at the moment when L is equal to 2, I need to know what is X. Well, to get that, I plug back into here. So I know that I'll have 1 plus X squared equals 2 squared when L is 2. So this is the same as saying 1 plus X squared equals 4. So X squared would be 3, which means X is going to be the square root of 3. I'm taking the positive square root here because I know X is a distance. It wouldn't make sense to say X is negative. The plane is flying in this direction. So when L is 2, X is root 3. Everything else I already know. So I want to find dl dt at the moment when L is 2. So from here we'll say plus when L is equal to 2, we have X, which is the square root of 3, times dx dt, which we know is 500, is equal to L times dl dt. That's 2 times dl dt. And we can solve just dividing over this 2. So we get square root of 3 times 500 over 2 for dl dt. And that's it. So the distance between the radar station and the plane, is this bigger or smaller than 500? Is this distance increasing faster or slower than the horizontal distance? I think it's a little bit faster because of the square root of 3. Oh, wait, no, root 3 is, yeah, no, thank you, slower. Yeah, root 3 is bigger than 1, but smaller than 2. Let's actually do the computation. Yeah, oh, an emulator up for the, shit, no. Yeah, let's see, as a decimal, where are we here? About how fast is this? Something from my college algebra group yesterday. We need square root of 3 times square root of 3 times 500 all over 2. Yeah, about 433. At that moment when L is equal to 2. So it's kind of fascinating, isn't it? Yeah, I might ask, why do I need this? Why is this at all interesting? Well, radar stations like to track the position of a plane. Yep, yeah, we've got the square root of 3 here times 500. The 500 isn't under the square root. Sorry if it looked like that. And then we had to divide over by this 2. Did I type something weird? Yeah, no, sorry. So the notation looks weird in the calculator, but you can write it like this: 500 times square root of 3. You'll see it's the same thing. Oh, shit, 500 times the square root of 3, all that, and over 2. It just looks weird in the calculator. You might ask, why is this important? Why is this interesting? Well, what's the job of a radar station? The job of a radar station is to have this map that tells you where the damn plane is, right? If you want to know exactly where this plane is, you need to know its distance from you. the straight line distance and the, from the station to the plane is different than the horizontal distance along the ground. And one of these is easy to track using instruments. L is actually easy to track using instruments. This L is the thing that the radar actually gives you, right? If you have a radar station that's beaming a signal out and you're waiting for that bounce back, the thing that you're going to get is L. It's not going to tell you X, but X is what you need in order to make your map and say where the plane is. So being able to figure out the relationship between L and X here is a big, big deal. And if you know how one is changing, you can predict how the other is changing. That's very important for radar stations that operate at, like at the airport, the ground control guys, they call it air traffic controllers. All of the hardware that they use are doing these calculations constantly. There's another one like this, where you have to find d theta dt. You have to find like how the angle in here is changing, and those are also really good. I'd like to do at least one more related rates problem with you guys before we wrap up the related rates examples. First, are there any questions on this one? Not too bad, right? Okay. Let's find one more. Something to do with some trigonometry, I think would be good, because we haven't done anything like that yet. Of course. That's a classic, but I want something with trigs, angles, there's got to be something here. Angle between the ladder and the ground. Okay. Yeah, this one is okay. Height is fine, not horizontal. What is the angle strain horizontal? Oh, 30 is fine. Okay, let's do number 30 here. Yeah, I like this. Because this is something most of us have experience with when we were little kids. So, okay. How is the I'm 200 feet strain? Okay. So our last little related rates example that we're going to work together. A little kid is flying a kite. So a kite is 100 feet off the ground, and it's moving horizontally at the speed 8 feet per second. We want to know, how is the angle between the string and the ground changing at the moment when 200 foot of string has been let out. I don't know why I drew this wall here, but we don't need them. That's not necessary for this. Okay, so here's my little kid. He's really, really tiny. He's on the ground, and he's flying a kite. Here's the string. Here's the kite. It's a kite. It has a tail. Looks nice like that. All right. I want to know if the kite is moving horizontally at a speed of, was it 8 feet per second? How is the angle down here changing at the moment when there's 200 feet of string out? So what we have to do is we have to figure out, again, we have to kind of set up a geometry thing. So I'm going to call this distance, I'll call it L again. Why not? L for the length here. And then we can construct another little right triangle. We can do it like that. Actually, since I've already drawn it like this, let's do it like this. Yeah. So you can imagine this kite kind of moving horizontally, right? And we're letting more and more and more string out to let this kite continue to move. Here's the height the kite is at, and we know that the kite is staying at 100 feet. So since the kite is moving horizontally, this is changing. So I'll call this X. Is it clear what's going on here? Little kid down here holding the kite string. The kite is 100 feet above the ground, but it's getting blown to the side. And the kid's there, he's like letting more and more string out. He's letting string out, letting string out, letting string out, and the kite just keeps flying to the side. We want to know, if I look at the moment when there's 200 feet of string out, how fast is this angle changing? So if you can imagine the kite being like over here later, that angle would be more shallow, right? And if the kite were way, way over here, that angle would be even more shallow. So what's going on with that angle? That's what I want. I want to know how the angle is changing. That's d theta dt. And I want that at the moment when L is equal to 200. I know, what things do I know here? Well, if this distance is x, and the kite's flying this way at 8 feet per second, then I know dx dt is 8. And I think that's everything we should need. I have some geometry here. And usually we've said, okay, so we've got a right triangle somewhere. I'm going to use Pythagoras. All right, we use a squared plus b squared equals c squared. This time, though, it's not going to be like that. Because the thing I'm after has to do with this angle down here. Which means I'm going to need to introduce some trigonometry. A squared plus b squared equals c squared doesn't help me at all with angles. At least not directly. I can look at the sine of theta, the cosine of theta, the tangent of theta, all of those things, and see which ones are going to be helpful to me. the sine of theta, that's the opposite over the hypotenuse. That's 100 over L. So if I differentiated with respect to time on both sides here, I would get cos theta times d theta dt. And over here, I'd have like, 100 times negative 1 over L squared dl dt. I don't know dl dt, and I don't want to have to calculate it. I'd like to work this out in terms of dx dt if I can. Let's look at the cosine of theta. Cos theta, that's adjacent over hypotenuse. This is x over L. And if I differentiate it on both sides, the left side here would become negative sine theta times d theta dt. The right-hand side would be complicated. It would require quotient rules and little chain rule stuff. This is a little scary looking. If we look at the tangent of theta, that's the opposite over the adjacent. That's 100 over x. So if I differentiate on both sides here, what will I get? On the left, I would get secant squared theta times d theta dt. On the right-hand side, I would get 100 times negative 1 over x squared times dx dt. I think this is the nice one to use. So we have to pick which trig function to use. Pick one equation to differentiate on both sides. You want to ask yourself what's easy and what gives me what I need. I need d theta dt. I need that. And the other thing I'd like is dx dt, because I know what dx dt is. I don't know what the other, like dl dt is. I don't know that. But I know that dx dt is 8, and I need d theta dt. So I'm going to pick the one that just has thetas and x's. That's this motherfucker right here. If we were really slick, we would use the cotangent function, because then I don't even have a complicated x derivative. That would make life really, really nice. But I think for now, if we just write down the 3 main functions and ask ourselves what's going on. Tangent is clearly the victor. So,
quick question. Why didn't we use the Pythagorean theorem for this? Or
because the Pythagorean theorem won't tell me anything about the angle theta in here.
oh, okay, yeah.
Right? My goal is to find how this is what I'm glad you asked this. This is precisely why we write down what we want. Right? As soon as we have our diagram labeled and everything, we write down what we want and what we know, and that kind of directs the choices we make from there on. So because I want d theta dt, I need to use a trig function, because otherwise I'm just talking about side lengths.
Yeah, okay, thank you.
Of course. All right, so let's go with this guy. This guy doesn't have x's. This guy has stuff I don't need. He's not easy. This guy is easy and has the stuff I need. So I'm going to apply d dt to both sides. On the left, I'll have d dt of tangent theta. On the right, I'll have d dt of 100 over x. On the left, I get secant squared of theta. That's the regular derivative, the derivative of the outer. And then I have to multiply by the derivative of the inner, which is d theta dt, because again, I'm differentiating with respect to the variable t here. On the right-hand side, let me clean this up a little bit. This is d dt of 100 times x to the negative first power. I think it'll be easier to differentiate like this. So the left-hand side is down. I've got secant squared of theta times d theta dt. And on the right-hand side, this 100 will just pop out. And then the derivative of x to the negative 1 is negative 1 times x to the -2. And then again, I'm differentiating with respect to the variable t, not with respect to x. So I have to multiply by dx dt. So now I have a relationship between d theta dt, the derivative I want, and dx dt, which is the derivative I know. I know that dx dt is 8. I want d theta dt. So by choosing this guy instead of the others, I end up with a differential equation that just involves the derivatives I know something about. This is good news.
Why didn't why didn't you take the derivative of 100?
Because 100 is a constant. Right, this is a constant multiple. It just comes along for the ride. You could use a product rule here if you wanted to, but you don't need to because 100 is a constant. The term in the product rule that involves the derivative of 100 would be 0.
Yeah.
So remember one of our early differentiation rules. We don't cite it explicitly a lot. I'll squeeze it over here. Here. But you know, if you prime a constant times f of x, I should say it like this, d dx of a constant times f of x. That constant just comes along for the ride, right? That constant multiple rule was one of our early rules. That's all I'm using here. Saving myself for work. Okay.
And then why did you just put in d theta over dt? Yeah.
It's a chain rule thing again, right? So I'm differentiating with respect to the variable t. So my outer function is tangent, my inner function is theta. Theta changes over time, right? Theta is not a constant. This does change over time. Remember we said if the kite's way out here, then this angle will be much shallower. So theta is a function. So when I want to differentiate with respect to the variable t, I differentiate the outer, leaving the inner alone. So that tangent becomes secant squared, and I leave the inside alone, which is theta. And then I have to multiply by the derivative of the inside. Well, the d dt derivative of theta is d theta dt. That's the thing I want.
Okay, thank you.
Now, unfortunately, there are some things in here I don't know, right? I don't know what secant squared of theta is. I don't know what negative x to the -2 is. I do know what dx dt is. But the x to the -2 here and the secant squared of theta, those are things I can figure out because they asked me to do all of this work to find the rate of change at the moment when there's 200 feet of string out. So plugging 8 for dx dt and simplifying, we get, what is this going to be? This is secant squared theta times d theta dt equals, I've got 100 here and 800 here. Sorry, 100 here and 8 here. That's going to make 800. I've got a negative here, so I'll write that as negative 800 times 1 over x squared. So I plugged in for dx dt. This is 8, and 8 times 100 is 800. 800 times -1 is -800. X to the -2 is 1 over x squared. So I need to know secant squared theta, and I need to know 1 over x squared at the moment when L is equal to 200. So to find d theta dt when L equals 200, we need secant squared theta and 1 over x squared when L equals 200. And this is a pretty common thing where we're going to have to come back here and redraw our picture at the specific moment in time that we're interested in. So here's theta. I know this height here is 100. My kite is always 100 feet off the ground. Here's x. And L at this moment is 200. So can I find x? Yeah, I can solve for x using Pythagoras. Can I find secant squared theta? Yeah, once I've solved for x. So sort of for this next page, I'll partition a little bit. We'll finish this work over here, and then we'll come back over there to finish the whole problem. So we know that x squared plus 100 squared is equal to 200 squared, which is x squared plus 10,000 equals 40,000. So x squared has to be equal to 30,000, which means x has to be the square root of 30,000. Which is the square root of 3 times 10,000. The square root of 10,000 is still 100, so this is the square root of 3 times 100. And that means I can come back here. All right, this has 100 times the square root of 3, so it's not confusing looking. And now I can figure out what secant of theta is. So secant of theta, that's the adjacent over the, cosine is the adjacent over the hypotenuse. So this is the hypotenuse over adjacent. This is going to be 200 over 100 square roots of 3, or just 2 over root 3. And now I'm ready to rock and roll. I can plug in the x value here. I can plug in for secant theta here. So if secant theta is 2 over root 3, then secant squared theta has to be 2 over the square root of 3 squared. Then my d theta dt is still here. Remember, that's what I want. And on the left-hand side, I have negative 800 over x squared. X is 100 times the square root of 3. So x squared is that squared. As we all learned on exam 1, secant, the square of this is 4/3. So we have 4/3 d theta dt equals negative 800 over, what is this? 100 times the square root of 3 squared. If you square that, you're going to get 10,000 times 3, which is 30,000. So you see a few things right away. I can solve for d theta dt. But at this step, we can tell definitely d theta dt is going to be negative. Here, I'll multiply by 3/4, so I'll have negative 800 over 30,000 times 3 over 4. And d theta dt being negative makes sense, because like we said, as that kite goes further and further out, that angle is getting more and more shallow. So theta should be shrinking. And it is. That's what we're seeing here. 800 divided by 4 is 200. 30,000 divided by 3 is 10,000. So finally I get d theta dt equals negative 200 over 10,000. And we can cancel several factors of 10, right? We can cancel 10 squared from this. So that is 20. Oh no, we can't cancel 2. Yeah, we can. That's going to be 2 over 100. Or we can even go further. We can cancel the 2 also, right? This is negative 1/50th. So theta is shrinking at 1/50th radians per second. That's what's going on here. Second. These are fun problems. These are really nice. Let me see if I can do it. So we chose, after we draw our picture, we chose the trig function that relates the 2 things I want, tells me how theta is connected to x, but doesn't have anything else in it. Then we differentiate on both sides. That gets us this. Let's see, yeah, I can zoom out maybe a little further. There we go. Let's do it like this. I'll move this down because I want you guys to be able to see also. I'll move this down. And kind of go through it a little bit. So questions up to here. All right, we drew our picture. We identified what we want, what we know, and then we had to pick which function we're going to use to relate these things. All right, you might consider taking a screenshot or something. I'm going to move this in just a second. Having chosen the trig function we wanted to use, we differentiate. So over here, we take the derivative, the time derivative, d dt, on both sides. On the left-hand side, d dt of tangent theta is secant squared theta times d theta dt. And on the right-hand side here, the constant multiple 100 just pops out. X to the -1 differentiates to -1 times x to the -2. And then we've got our dx dt also, right? Same as we got the d theta dt. We're differentiating with respect to time. I know that dx dt is 8. So I go ahead and plug that in here. And then I ask, well, what don't I know? D theta dt is what the thing I want, but I don't know this piece and I don't know this piece. So we came back over here and redrew our triangle. We redrew our triangle at the moment in question when L is equal to 200. When L is 200, I know that this is always 100. They said the kite is always at 100 feet above the ground, it's just moving horizontally. So when L is 200, I can solve for the missing side down here. We did that. I'm going to move the paper. And we solved for that missing side, and we found that that missing side was 100 times the square root of 3. So now I know the x that I have to come back and plug in here. That's going to be 100 times the square root of 3. I also need to know secant squared theta. So looking at this triangle, secant of theta I know is the hypotenuse over the adjacent. That's SOHCAHTOA. Cosine is adjacent over hypotenuse, so secant is hypotenuse over adjacent. So secant of theta has to be 200 over 100 times the square root of 3. We cancel the 100 and we get 2 over root 3. We plug that in here. All right, secant squared theta is 2 over root 3 squared. And from there, we just clean things up. Might consider taking a screen cap here if you want it. I'll move the page in a second. And here's the last little bit where we kind of wrap things up. So having plugged in, simplified, solve for d theta dt. D theta dt is -1 over 50. The units of theta are radians. The units of time here is being measured in seconds. So this is radians per second. D theta dt is -1/50th radians per second. which means theta is shrinking at a 1/50th radian per second. Or every 50 seconds, theta goes down by 1 radian. And that's it. So you have a few of these related rates problems in your homework. I promise you there will be a related rates problem on exam 2. There absolutely will be a related rates problem on exam 2. Also, if you're going to study any sort of physics or engineering, this is going to be your bread and butter. These sort of expressions here, like this, where is it? This, they're called differential equations. And differential equations are the language in which the universe in physics is really written. And it's about how one rate of change affects another rate of change. All right. That's all we have time for today. I'm afraid we got to get going. I think we're actually a few minutes over time, so I appreciate your patience. I will have my normal office hour today. If you have any questions, you can come by and bug me there. Not that you're bugging me, it's not like that. I'm just being silly with words. You can come visit me in office hours with any questions. Otherwise, you can Canvas message or email me. If I don't see you on any of those things, I will see you guys on Monday. Take care. Make sure you work hard on that homework.